Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for Quest 17 of Everybody Codes 2025. Been having a lot of fun. This one was a fun one. A little crazy. The third part of the problem, I think, well, we'll see how other people solve it. But I think this is one of those things where if you know how to do something, it might be easier than if you don't. Anyway, we'll see how other people solve it. I think there's possibly other ways to do it, but I had I happen to know about. Well, I'll just give away the secret. There's like a winding number trick that you can use to calculate a loop, and I happen to know about it. I did have to Google it to copy some code, but the code's actually not that complex. See it, so. But I happen to know what the algorithm was, so I went and found. I actually don't remember if it was my own solution or someone else's problem before, where it was like we've had a similar problem like this where you're doing path finding, but the path finding has to make a loop. So anyway, that's where it came from. I think it was a previous solution we've done. It wasn't everybody codes, it was an advent code. So anyway, it was a fun day overall. The way that the story starts is you're with that the special order of duck protectors. I can't remember what their name was. Anyway, a volcano starts to erupt, and so everyone's freaking out about the volcano. And so your goal is to like use your skills to try and like save the people from the volcano. And so that's where like the story evolves. So for part one, the thing that they want you to do is figure out like, and it's kind of a setup one. The idea is, can you calculate the lava flow of the volcano? So the volcano starts here at the center, and the question is like, can you calculate how much of the grid it would cover at different radiuses or radii? They actually give you the formula right here. So I think this is an interesting one because it was this one you're actually kind of calculating the Euclidean distance, right? Like the actual circle, the Euclidean. Am I saying that right? That you're actually calculating a circle to determine if this value is inside that circle. Whereas a lot of times with these grid style things, because they're like points in a box, they usually do like Manhattan distances. The Manhattan distance, though, would make it more boxy, and so I think they just made it more interesting. It turns out either way would have been like relatively easy, especially because they actually give you the formula. So part one is literally just, can you do this formula and then find these values for r equals 10? And so what you do is you kind of just go through the grid and you say, okay, well, is this one in the radius? If it is, what is its value? Then we sum up, you kind of get a circle like this, and then you sum up those values and it gives you a number. Sum up all these single digit numbers and it gives you a value. So that one wasn't too tough, I don't think. It wasn't very hard. I'll show you. I actually did a lot of like weird work for multiple parts, but I used a tile. I think they called it a tile in the problem is probably where I got it from, but you're just tracking the row and column. I stuck with eye sizes so we could do bounding boxes in the grid, and then you'll see later I use like a get helper function to convert those eye sizes to U sizes. I feel like that kind of made it more easy to like grok what's happening. But then otherwise I just need to parse a grid, right? So you give me a string and I will parse it, and I'm going to turn that into a set of tiles, or I guess a 2D array of tiles, and then the volcano, and this start is for part 3. So but the gist is I'm just like creating a 2D array. Notice I use 0 eye size and zip it with input. I think I've done things like that before from a previous commenter that had mentioned this is an easy way to like enumerate, but maybe you want eye sizes or you want to start at 1. I think this is a cool way to do it. So it looks like an enumerate, but you're enumerating with the right values. So I kind of like that. But then otherwise, I'm just creating the grid. The only extra check I'm doing is like the @ sign is the volcano location. And then in part 3, the S is the where start for part 3. We'll talk about that more later, but that's just the grid. And then I had some helper functions here where, give me the height, the width, what is the maximum. I don't think that's used. Oh, it might be used for part 1 and part 2. And then get that position. This is what I was talking about, is like, it is, you give me a tile, I'll get the value at that tile, and I just, convert the sizes. For me, it kind of made it easier to understand. I don't know, you can go one way or the other. I think when I was originally doing it, I just had this like in the code, but as I was refactoring, trying to make it more readable. Anyway, the idea is you have a bunch of these helper functions, right, that are kind of showing you, that make it easier for you to just say, oh, what's the height? What's the width? What's the max height width ratio? And then what's the cost at that specific thing, right? So the volcano itself and the start position are zeros. And so that's what that is. This is, at first I think when I had originally solved it, I just had like 0 through 9, pouring them together. But I realized you could do is ASCII digit. So this if thing, I always forget these ifs and like wheres and stuff like that. In this time it occurred, I can just say, is it an ASCII digit? If it is, convert it and unwrap it. This is a comparatively safe unwrap because it's already verified that it's an ASCII digit. So this might be a case where you say, I'll allow this unwrap if you're worried about unwrap gate in your code. Then we just need to make the in radius function, right? So if you give me a radius and the center position, the position of a tile, I should say, I'll tell you whether or not it's within the radius of the volcano. And we're just using the code that they gave us, right? So we take the absolute value of the row to the volcano row and the column to the volcano column, and then we just multiply those and make sure it's less than or equal to the radius squared, right? This is a known mathematical thing, and so you basically just take what they gave you and do it, right? It's not that hard. So then you just have to calculate like what the level of destruction is at a given radius. In this case, in part 1, you're doing it for radius 10, but here's how you would do it. For me, I was like, I can just create like imagine creating a bounding box around. I mean, the example problem isn't great for size 10, but imagine the grid's like substantially larger. Maybe I have one here. Like, say you were only counting it for like R3 right here. You'd kind of create like a bounding box around this thing right here. So the bounding box would look like this. These are the only values that are like worth checking, right? And so you kind of create that bounding box and say, I'm just going to check all these values and see if they're within the radius. And if they are, then I count them towards my. So that's all that's doing is we calculate we do a Cartesian product to get the bounding box. And then obviously we don't want to do the center position, although now thinking about it, that position would have returned 0, I guess. But then we create a tile based on the volcano's own column plus the deltas. And then we just ask ourselves, is it still in the grid? And is it in the radius? And if it is, we map it to its cost, and then we sum all those values up. And that will give us our total destruction for that radius. And so that's all you do for part 1. I was able to simplify it to this one line, right? You just parse the grid, calculate the destruction. You'll notice I've removed some of in my template for the quests, having the multiple part things didn't seem helpful. So I just passed the input thing now right here. See, I have these, and then I just pass the input. So I parse it, and then I calculate the destruction at 10, and that's for part 1. Not too tough, right? Just follow this and do it for the bounding box. I suspect the grid is small enough that if you did it for the whole thing, yeah, it is relatively small, right? So if you did it for the whole thing, it would just, it may be a little bit more time to solve, but not substantially more. So it was a very minor optimization of saying only calculate the bounding box. And especially if I didn't even look, is the bounding box 10? It's a little bit higher. It looks like it's 15. So it is a minor optimization. But anyway, that was something that came to my mind as I was solving. On to part 2. So what happens with part 2 now is they say, oh, I want to figure out like which radius has the biggest effect of destruction. So the idea being is as if you start at R1, it does these 4 values and those sum up to 26. And then the radius of 2 is like these values right here, which are, what is there, 8 of them? Yeah, there's 8 of them. And so those 8 values do 49 damage. And then these values right here do 109 damage. These values here do 146, right? And so you want to kind of calculate how much damage is done at each radius, and then return the largest one is essentially what it is. It's like, so find the largest one and return it as a product of the radius. So in this case, over a span of 6, you get the largest one was 218 and its radius was 5. Multiply those together, that gives the answer. I don't think this one caused too much trouble for me. I did have to refactor. I think I did a little refactoring. We'll look at the times in a minute, see what happened. But I don't think this was too tough, because the thing that was going through my mind was, and I imagine most people was, oh, well, if I start at my current radius of 1, my next radius of 2 is just the destruction of 2 minus the destruction of 1. And so I can kind of track each one in a window, right? So I just kind of keep a window, a sliding window of 2, and track those, and whichever one's the biggest, I can do that. So here's what that looks like in code. I can I create my grid, and then I can reuse my destruction thing, but so first I map my radius to my radius and my destruction. So now I have, 1 and the destruction caused at 1, 2 and the destruction caused at 2, so on and so forth. Then I create tuple windows. This is like a thing from iter tools. I think we've used it before, right? It's going to take the iterator and do it in like a sliding window of 2 tuples. So I just take I have my first one and my second one, and I just say, okay, I'm going to map that to my second radius, and its destruction is the destruction of this one minus the destruction of the previous. So now I get the destruction for this specific one. Just that outer ring is maybe the way to think about it. Like the total destruction is like this value right here, right? But you want to remove the destruction right here. And so that's the idea, is this is R2 and this is R1. And so the idea is you're just going to remove R2 from R1 to get your values. And then max by key, we've learned this before, again, from a commenter, I think. Maybe I've heard it before, but we literally just map through them, find the maximum destruction and unwrap that. So now we're going to have our maximum radius and destruction. We just multiply those together to get. So there you go. Not too shabby. I thought it was, I thought this one like felt good because you could do it really easily as functional. And so it maybe take me a little bit of time to like get this right as I was coding it, but I did feel like, okay, very cool, not too hard. Oh, and again, I don't think part 1 or part 2 were meant to be particularly hard. Part 3, I think, took me probably the most time to solve because it was the hardest part. Speaking of part 3, what happens in part 3? Well, apparently there's a plant that can stop the fire, but the plant has to make a loop around the entire lava flow, and it has to make a successful loop around the lava flow before the lava touches it. And so they call it a recurlia loop. Now I wonder if that's actually a hint. Recurlia. I actually don't know. But like, I think it will make most sense if you actually look at it. Oh, there's one other gotcha that you just need to keep in mind. The lava increases its radius every 30 seconds, and the cost of moving from one position to the other is this actual number right here. So to go from here to here, it's a cost of 4. From here to here, it's a cost of 5. Here to here, it's a cost of 3, so on and so forth. And so the idea is, can you successfully make a loop by the time the lava has expanded to that point? So they give you some good examples, right? So they say, oh, if you try and solve it by lava before the lava has even started to flow, so in the first 30 seconds, you can only get to like right here, and then the lava flows and breaks it. And then they say, oh, but if the lava is at level 1 or of radius 2, I guess, whatever, you can go this far. This is like the shortest path, and but you won't be able to make a whole loop before that gets through. So you try it again at radius 3, and here's the shortest path. Try it again at radius 4, here's the shortest path. Try it again at radius 5, and boom, finally you can get to the end. So, and it says, okay, so now you found this like shortest path that creates a loop around the volcano and lava. And what you do is you take the number of seconds and multiply it by the radius of the volcano to get you there. So that part is incidental. Presumably, once you've solved it, you can take the number of the total distance traveled and multiply that by the radius. They give you a couple other bigger examples, right? So they say in this one, even though the grid's a little bit bigger, you can kind of make this loop at radius 3 and solve it. And then at this one, you can kind of make this loop to solve it. So it's a much bigger problem, and you can make this loop to solve it. So how do you go about solving a problem like this? Well, it probably occurs to you that you could use Dijkstra's to like find the shortest path, and that's what I ended up using. I didn't implement it with the pathfinding. I believe you actually could use the pathfinding crate, but there was enough weird logic about and I did further refine it, so it might be simpler to do now. But there's some logic about like determining where you want to go that didn't seem to like at the time it felt kind of fuzzy of like, could I just put this in a successors function, like the neighbors function? And so I implemented Dijkstra's on my own. But again, we've implemented that before, so I won't go into too much detail of how that works, but you're basically just finding the shortest path. And because you're always preferring, or because your frontier is always picking the shortest path that you've traveled so far, once you've found your end point, your quote unquote end, you found the shortest path because you've only ever taken the shortest path to get there from that point. That's Dijkstra's in a nutshell. So I think the real question then is, if you say to yourself, oh, well, if it was just Dijkstra's, that would be pretty easy. I mean, comparatively easy. The hardest part, I think, was how do you know if you've made a loop around it? And that part was I could see being an issue. So I'll be interested to see how people felt about this day. I happen to be aware of, I think we've solved this before with other things where you're trying to like see if a point is in a polynomial, or see if a loop is created around a point, which happens to be this case. There's some of these puzzles where you kind of do this, and the way to track it is called a winding number. I think it's called a winding number. I'll show you how it works. The idea is, here's your grid. So this is like the solved path for the small solution. If you break up your grid like this into quadrants, so like this, that's a terrible line, I apologize. If you break it up like this and you consider this quadrant 1 and this quadrant 2 and this quadrant 3 and this, or I may have maybe doing that in the wrong order from my actual code, but let's just break it into these quadrants. The thing that will tell you if you've like quote unquote done a loop is if you visited, you know, all quadrants. So a loop equals, you know, visit all quadrants, right? So the question you just have to ask yourself is, well, how do I know if I visited all quadrants? You could kind of track that, but the cool thing about the winding number is that it will do it for you. And the idea is you just track every time you cross a border. So every time you go from here to here and you cross a border, or here to here and you cross a border, or here to here, or here to here, or backwards too, right? Here to here, or here to here, or, you know, here to here. And it can go back and forth too, right? So say you go here and then you go right back over to here. You just want to track those border crossing. And the idea is clockwise is +1 and counterclockwise is -1. So if you've crossed a border that's caused you to go clockwise, you go +1, or counterclockwise -1. I actually think in my solution I'm doing the opposite, but just the idea will be the same. So I think so. We'll look. I forgot what's in the code, but the idea is you're just tracking, are you going clockwise or counterclockwise, and then you just sum those up. And so now what you can do is really cool, is you just add those up, right? So if I cross here, I go from 0 to 1. And then if I cross here, I go from 1 to 2. If I go back, maybe I go to 1 and then to 2, and then now I cross here, I go to 3, and then maybe I go back, so I go 2, but then I go back over, now I go to 3, and then when I get here, I now go to 4. And if I ever like have found the start position again and I'm at 4, I know I've solved the problem, right? Because if I ever hit the start position and my winding number, I looked at loop and I wanted to call it a loop number. Maybe it is called a loop number. I think it's called a winding number. I called it a winding number but the idea is if I've wound around, I know that and I'm at the start position again, I know that I've solved the problem. It also works in the opposite direction, right? So if you're going this way, it works, but it also works this way. You just have to track. It just is like the opposite would be -4. So if you've ever gotten to any of these, 4 or -4, it's solved, or maybe solved isn't the right way. The loop is complete. And again, the thing about this is, oops, I definitely didn't want to delete that one. The thing that I kind of want you to like keep in mind here is that the reason why this like loop I've got loop stuck in my head now. The winding number is so cool is because the path can, and it won't, I don't think it'll always do this, especially like in this case, it doesn't. But it's possible that the shortest path is something like this, and then like this, and then like this, and then like this, and then like this, and this, right? So you can have these winds in it, and that's okay, and it still actually creates the loop for you. That makes sense. So it will still say, yes, you've made a loop, because the net effect of going clockwise or counterclockwise has moved you around the clock. So I think that's what makes this relatively easy to solve. At least for me, it is to say, oh, I just kind of track my winding number. Have I wound myself sufficiently? Have I found the start position, and have I wound myself sufficiently? So if I haven't found the start position and I haven't wound myself completely, then I know I'm not at the end. So that's how I have to solve it. So then the question that the last question you have to ask yourself is like, okay, I know I need to do it with Dijkstra's. I know I can use the loop or the winding number to find the loop around the volcano. And then the third question you have to ask yourself is like, well, how do I find the right radius? And I actually don't know the answer to that. We had just done a problem where binary search worked, and it happened to be this answer to the whole part. If you go back and watch that video, I just took the use all my processors approach, because looking at the problem, like if you actually look at the input, it is fairly large, but I mean the radius, the total radius, isn't more than like 30. So I presume in parallel I can just calculate all 30 of them and find any of them that are successful, and then find the smallest one, the smallest radius that it's successful in, and then calculate its loop. Or I will have calculated its loop so I can get those values. And so that's what I did. So those are the key things: Dijkstra, looping with winding numbers, and then I did mine in parallel. I actually, again, there might be a better way to solve that last part, but we'll. So what do we need to do? Well, I added this to my grid. I said, okay, for the grid, I want to know where my obstacles are, and that's going to help me with Dijkstra's algorithm, right? I can now say, do I am I within the radius of, or is like the lava flow? Well, the lava flow, excuse me, is the obstacle, and so I obviously can't go through the lava flow, and so I just want to track that, and I do it as a hash set of tiles. So I can do a simple comparison and say, hey, as long as my neighbor's not in there, then I can do it. Now we need to track our loop state, right? So this is how we're tracking whether we've made a loop. And the way we do that, this is also used in like the node, or like the node of the graph for Dijkstra's. So I just want to track what quadrant I'm in, right? And that's like 0, 1, 2, 3 or whatever. I want to know how far I've wound. So this is my winding number, right? And and I'm looking for a number between, it's going to be between -4 and 4. So eventually I'm going to hit one of those values. And that will be like quote unquote complete. And then I need to track my current position, right? My current position will help inform me what my neighbors are, but then also what it will help me update my winding number and my quadrant. So I have a new function because at the beginning of the Dijkstra's, I create a bunch of empty ones with no winding. And then I just have these helper functions that determine the delta between the two quadrants. So if I'm in quadrant 1 and I'm going to quadrant 2, if I do 2 minus 1 rem Euclid, that gives me 1. That's clockwise. But if I'm in like quadrant 2 and I go to 1, that gives me a -1, which puts me at 3, which means I'm going counterclockwise. Otherwise, I'm in the same quadrant, so I just put 0. I think in the general case, this also technically happens when you're going across a quadrant. We can't do that in our case because of the loop, because of the obstacles, right? The lava is obviously in the way, and so we never actually get there. And then I just have a helper function to track my next state, right? So given my current state, if you give me the neighboring tile and where the Kano's start is, I can tell you, and this is to calculate what quadrant I'm in, right? So I'll show you, where's that quadrant function? Maybe did I skip it? Yeah, so right. Well, here's the two functions in the tile, right? Here's my neighbors function, where I basically just go through all my neighbors and make sure they're valid, like, and then I return an iterator of those neighbors. And then my quadrant is basically just a check, right? Given the center tile, where am I with respect to that center tile? Am I at the top right, bottom left, or top left, right? So and these are kind of did I do it in the right 0 1? Well, I did it ones based in the thing, right? But top left, bottom right, top right. Yeah, so I think I did it the same way I drew it. Anyway, that quadrant is going to tell me where I am, so I can do this kind of math right here to see where I've moved. So to get a new state, if you tell me what my neighboring tile is, I can figure out what my neighbor quadrant is, and then I can, my new position is the neighbor. How I've wound is my winding plus the delta, right? So if I've currently wound 2 and I wind one more, I'm now at 3. If I wind back, I'm now at 1, right? So that's tracking that. And then I just keep my neighbor quadrant here. Yeah, that probably is more readable. And then I just need to check if I'm complete, right? Is my winding complete? That is if the absolute value of the winding is greater than or equal to 4. So it could be 5, right? Technically, the shortest path could have you go 5, for example, or -5. Like the case where that would happen is if like the shortest path, I've really mucked this drawing up, but imagine the shortest path goes here, here, and here. Like that would give you a number of 5, but it would still be a valid loop, right? Because you've crossed it over. So then we just have to have a node to track our Dijkstras. And what is that? That's the cost to get to this node, the current cost that we know about, and the state, which is what we've talked about before, that has the winding number in the tile we're on. And then we have the previous tile, right? So this is just for like performance stuff. Like when I tested it with and without, tracking the previous state and the start position, like, because you never actually want to go back to the start until you've made a full loop. And so you'll see my Dijkstra's looks kind of funky because of that, but I actually found that this again, a lot of this was me after I've solved it trying to optimize it. My initial solve, because I hadn't done the rayon either, the parallelization, I think it took like 5 or 6 seconds. And so this is me doing refinement after the fact to, I had the same idea, the similar thing. I had a winding number, I was doing Dijkstra's, and I was, checking if I've wound all the way, but I wasn't doing in parallel. It did solve it, but it took like 5 or 6 seconds. And then I was like, okay, well, I guess I should try and optimize this because I don't. And a lot of my optimization, most of it was just using rayon. So I don't know if that counts as me like doing cool optimizations, but that's the first thing I did. Then the next was, I think so that was the biggest optimization, was just parallelizing. But tracking the previous tile and making sure you're not going back to the start happened to save like 15 or 20% of the time. You'll actually see these times, they change pretty wildly. And I think it has to do with how rayon's working. And also because I'm recording, like, I think it's sometimes it will get to like 50 milliseconds where it will solve. I don't know how that compares to everyone else's, but then sometimes it's like 150. And I've noticed as it's been happening, as I've been recording, the numbers are a little bit higher. But this is our actual Dijkstra's node. The only thing to note here is, like, this is just like any Dijkstra's, where you could have potentially just tracked this in a tuple, but you actually want to do a comparison on it. And because we want to do the minimum cost, we need to like reverse this comparison. And I think we've done this before, right? Is where we've said the basically the easiest way to compare it is, or to do a min heap, is just to say the other cost comp my cost, and that has the effect of reversing it. Normally this comp would be self cost comp other cost, but because we're doing it this way, it like has the effect of creating a min heap for your binary. We just have to implement these in our node so that we can do that. And then this is Dijkstra's, right? So we do Dijkstra's algorithm on it. So we want to create our frontier. Note it's a binary heap here. So we start by adding all the neighbors of our start node, right? So we create all of our neighbors and we filter them by ones that aren't in the lava. I didn't think this would ever be the case, but it's possible it is. And so I added this in here. Like, it's possible that the fastest loop would be if the lava was like at the start position and you could only go like left or right. That makes sense. So like it's possible that the lava goes to right here, and so like your only solution, I should like this, the lava's right here, and so your only solution is to like go this way. Okay. So yeah, this is just me like setting up my initial state, but then we also want to track our distances. So this is like so in Dijkstra's, you want to track how far you've gone at every state, at every loop state, not the node state, the loop state, just to be clear. You want to do it at the node state. That makes sense. And the reason you want to do that is because if you ever get to a node, so like, maybe I should do this up here so it's a little bit easier, but like, let's say you first visit this node and it was 24, and then somehow you've gotten back here, but now your new distance is 17. Well, you'd actually like to now revisit this path at 17 because it may give you a cheaper path to get there. And so that's why you need to track your distances. This is a little bit like if you're doing a BFS, this is like your scene list. In Dijkstra's, it works slightly different because the cost could be updated, and that would help you infer whether or not you want to like revisit that path because you found a shorter path. But otherwise, this is a lot like a BFS, right? Because the difference is, I mean, it's not like, it's more like a DFS, I guess is the way to say it, because you're actually always trying to visit no, it is like a BFS because you're always trying to visit the shortest path. And so depending on how the structure is, it will do more branching until it finds the thing, until it finds the solution. I mean, I guess it's a hybrid. It's not really one or the other, but it's closer, I think, to BFS. Anyway, all that saying, we're just going to now go through all of our neighbors. We're going to check to see if we've seen this one before. And if we have, and it's not better, then obviously we don't need to track this. Otherwise, we want to add our distance to our state. And then we want to get each of our neighbors. So we use the neighbor functions above. And then we just ask some questions. First of all, we say, well, is this the end? If the neighbor is the end, then we know we're done, right? We solved the problem, we're done. No need to continue. And so that's two things, right? We're back at the start and our state is complete. That is the have we wound all the way around is the way to think about it. And then we just want to make sure we don't do backtracking. This is the part I was talking about that happened to save, I don't know, somewhere on the order of 20% time, where we say, okay, well, I don't want to go to my previous node. I don't want to go to the start node. And obviously this one would always be there, right? I don't want to go to a lava node. I can't go there. So, but these two were mostly just for performance. Otherwise, then we just pop our neighbor node on the front, right? And then we're done. So that's Dijkstra's. You do that recursively for all the neighbors. You're slowly branching, finding the shortest path until you've like come back to the start where you're now there. Well, you've come back to the start and you've completed a loop, then you're done. So what does part 3 look like? Again, here's just where I parallelized it, right? So I go for each of the radiuses and then I say parallelize this, we do a filter map where we say find the shortest loop for that radius. This is like, I realize this looks a little ugly, but using filter map, find shortest loop could return none, right? If you remember the problem, it was like some of them, not all of them, return a path, right? So, radius 4 doesn't solve, like you wouldn't be able to solve this in the time. You can find a shortest path, but it doesn't solve it in the time. And so, um, the none is here just to say like maybe there's not a shortest path, but then you also have to filter it by, is the time less than the radius, less than or equal to the radius, right? So these two have the effect of saying find the shortest loop and make sure it's within the radius, or within the time frame that the lava would have expanded over that. And then we just map that to the time and the radius and return the min, and we're done. That's the find the smallest and we're done. Now that I think about it, this map may be incorrect. We may have wanted to do like maybe the more technically correct way would have been like the by radius. Uh, filter. Okay. Yeah, I did fix that. Technically, this is the right way because I think you want to do it at this. I think the problem says like do it at the say find the fastest way to create a recurlia loop around the volcano to get the final, multiply the number of seeds by the radius of the volcano at the moment it closes. It may have been one or the other. It might be that they're actually both the same. The impression I got was the smaller the radius, the better. If you're thinking about land destruction, you want to like stop it at the smallest, but who knows? It looks like both they both solve either way, so I'll leave this in here how it is. Okay, so hopefully that makes sense for part 3. The gist of my solution was Dijkstra's plus winding number plus parallelize for efficiency, and that gets me into this. Again, it must be because I'm recording that it's like taking twice as long. I suspect what happens is I just, every time I run it, I blast all my CPUs in parallel doing Dijkstra's, and then this resolves that. Anyway, that's it for me. Should we check the progress now to see how it happened? I think this day was somewhat difficult. We're definitely into difficulter days, more harder than like 1, 2, 3, 4. I suspect these last few days are going to be pretty hard. So this one was a lot harder. It was not as hard as day 10 for me, at least. We don't talk about day 10. Oh yeah, now I'm definitely scaly. I'm a dragon duck. I'll be interested to see what my final. Yeah, we're just 3 away. What it looks like at the end. Okay, so let's look at my times. Again, just as we're doing these times, don't look at my code and think, oh, did he really do that in... Okay, so it took me about an hour to do. And again, I was like, it looks like about 2.5 hours late. Do not look at my time and say, oh, how did he write that beautiful code in that much time? I solved it, and again, like I said, it took like 7 seconds to solve, and then I've spent 3 or 4 hours since refactoring it to try and make it more readable and make it more consumable as like a video. So hopefully that makes sense to you. So yeah, part 1 wasn't too tough. 16 minutes, and then another 15 minutes for part 2, and then a half an hour for part 3. This one could have easily been longer, I think, if I had not known about the winding number. I did think briefly about like what are potential alternative solutions. I don't know if I don't have a good graph. Can I like take this and copy it? Uh, okay, so I had a couple other thoughts about what might be a potential solution to like solving this. If you notice all the puzzle, like in the puzzle itself, the way that it always solves is like, at least the examples they give you is here, here, and here. So I think there's a potential for, and I don't know if this works for the input because I actually happen to know about the winding numbers. But as I was implementing the winding numbers and looking, because I was like, when you're solving these puzzles, the thing that I always think about, because I'm not smart, I guess, I don't know, is I say to myself, okay, if this doesn't work, what could be something else I could do? So while I'm implementing the winding number and I'm looking at the puzzles and I'm waiting my 6 or 7 seconds every time I try it, I'm noticing that it solves like this. So there is possibly a potential to say Dijkstra from here to here, find these 3 numbers, Dijkstra from here, and then Dijkstra to here, Dijkstra to here, Dijkstra to here, and that gives it to you. I don't actually know if that works for the general solution, or well, it probably doesn't work for the generalized solution, but it's possible that the puzzle input could do that. The other thing is, if you notice, my Dijkstra is actually reversible, so it's actually going both ways as it's doing it. And one optimization that I was interested in doing, but I haven't done, maybe this will be for for the recap or whatever. If I'm tracking my distances like here, if I could track if I'm coming from this way and this way by my winding number, right? If I'm winding like this way would be a 2 and this way would be a -2. If I hit a number that is -2 and my current one is 2, like I've seen this distance, this 6 before at a -2, and now I've hit it at a 2. I actually know the sum of those paths is what gets me the answer, and I can stop. So that's an interesting optimization that I've wanted to try. I've just run out of time to do it today. Is like, if you're going from this side and your winding number is -2 and 2, that could say, oh, this is actually the solution here, and then that would get you. I think you could also potentially do that with doing a Dijkstra from here to any node right here. So you say do a Dijkstra to like these 3 nodes, and then do a Dijkstra on this side to these 3 nodes, and then you just pick whichever one gets you the minimum distance around the thing. So those are other potential solutions that like came to my mind. Again, they're all very heavily focused on just doing Dijkstra. It's just, how do you do your Dijkstra? And so it's not clear to me that there's another way to do it. But I mean, we'll go check. We'll find out. Maybe there are other ways. So yeah, I think an hour isn't too bad for this one. Again, heavily refined. After the fact, I've spent several hours, refining my code. So this code that you're looking at right now, it looked. I mean, part 1 and part 2 were pretty close. I had this parse function, I think, and this destruction thing looked close to this. I think at the time it may have been doing a filter map like with these 2, but this felt more readable, so I changed it this way. I did have this to begin with for part 2. A lot of this, like, I think at the time my obstacles, it was like actually in the find shortest path. this one felt, I actually think this one made it faster too. Like I think my original solution was actually just getting a point and determining, or getting a neighbor and checking, is it in the radius, and then considering it not valid if it was. But I think this way was actually faster, so I left it this, and I think it's more reasonable, right? This is a very common thing with Dijkstra, is you say, hey, keep a list of like quote unquote obstacles that you can't pass. Okay. Loop state, I think, was something that I'd implemented. It looked a little bit different than this, so I did do some refactoring here. I had this next state function. My is complete, I think I didn't actually have this. I just checked it was the winding ABS at the time, but I feel like that makes it more. I could actually rename this too. It probably makes more sense to say this winding complete. Yeah, the nodes. I mean, if you're doing Dijkstra, you kind of have to implement these nodes, the order and partial order. And then the Dijkstra is a pretty known thing. So again, I think what changed this, I was able to, I don't think I did this originally. I did it in a for loop. But again, you can collect on some of the data structure, or most of the data structures in the standard library. So I changed that. I should remember to do this because this, at least in my mind, feels more readable than the for loop. And these optimizations I didn't have, like tracking the previous node, or I guess down here, tracking the previous node in the start, weren't there to begin with. But it happened to be like, it actually gave me some significant enough optimization that I stuck with it. And then this was my initial implementation, the one that took 6 or 7 seconds, was just in a for loop. I started at 1 and worked my way up until I found the right one. And that's what took 6 or 7 seconds. Because like you can see, like each Dijkstra probably takes, around 100 milliseconds or whatever. At the time, it was probably closer to 200 milliseconds. And then if you take into account that you're probably doing that, I don't know, 14 or 15 times before you find the right one, that's a lot of time, right? So you can see why it would take 7 or so seconds. There you go. I think that's about it from that. So let's go. I want to go look at the solution, see what everyone else did. Look curious. Got a lot of comments. There's a super nice solution, part 3, winding numbers. Okay, perfect. Winding numbers is great. At least I was on the right track, right? Oh, okay. It's like, it looks like what's happening here in this for loop is, obviously we're going through all the values and we're saying, as long as it's not the volcano, and this is less than or equal to this, and is less than or equal to that. So like the idea is you're kind of creating a bounding box, right? So like you don't want to go inside the inner radius or outside the outer radius. And then otherwise you calculate your distance. So that's cool. That's an optimization. Again, if you remember, I did mine kind of in Windows, tracking the previous one and adding the next. In this case, they're saying, oh, just make sure that I'm not in my inner radius and I'm not in my outer radius. Okay. We implement a priority queue and do Dijkstras. Where's the winding part? Okay, this is the more traditional Dijkstras where you like fill up the whole grid and you have unvisited nodes and you're updating your unvisited values with their distances. So this one's straight. Like if you go look at the Wikipedia, it looks exactly like this. Right? Okay. Okay, yeah. Again, this is what I was thinking: is you could do two Dijkstra calls for the left and the right side. But again, the winding number is very cool. This does have the effect of doing Dijkstra twice because you're actually doing Dijkstra on the whole map. Like I had mentioned, you're actually going both ways as you're filling it out. And so again, I think there's an optimization where you could say if I'm ever here at this center grid or at the center line and I've seen it before, I probably and I'm -2 and 2, that means that I've like solved it. And so that's definitely an optimization. And I think that's what they're saying here, right? Like this has the same effect. I had a similar approach with additional state variable defining delta as the cumulative angle from the start position with respect to the lava pit. Path completely encloses for at least 2 I star. Oh, okay. So you're just tracking like your angle at each position, and so this has the same effect, right? Is like as you're moving up and down angles, it's reducing or increasing it, but then eventually you get all the way around and it does it. I would actually be interested in seeing this because maybe we'll find it later. It may be weird. There's like float arithmetic you have to do that you just have to make sure it's all. Okay. A lot of people use imaginary numbers here for like rows and columns. That I've seen that solved before. Very cool. Video me solving. For part 3, I compute left and right. Okay, I think this is a little bit like what I was talking about. Is like there's a potential for you to go down the left side and the right side, which was talked about up here, right here. Yeah, I think there's okay, so that's definitely a way to solve it too, is to go left or right. Oh, is this them solving the problem? Yeah, part of me wonders if it actually, if like the other one I had mentioned is like there's the potential to say to like Dijkstra from here to here, and then from here to here, and then here to here, and then here to here. Oh, but look, see here, that actually doesn't solve it for this case. So it's quite possible that that's not the actual solution. This GIF is actually kind of cool. Sometimes it's nice to visualize these things because in your head it's not always clear, especially with an algorithm like Dijkstra's. like what's happening. Brute force checks for part 3. The grid is modified by drawing a vertical wall to divide the grid in 2. Then 2 Dijkstras are done to start position. So, okay, so I think this is the other way, maybe just implemented slightly. This is the way I was talking about. I think you can probably Dijkstra on either side. Doing it for all radius. Yeah, so like you do Dijkstras on both sides. If you ever, obviously, if either of them don't solve, you continue. Otherwise, you'll get your total distance, and that will give you your best one, and then you return that. That is a good point because you're trying to find the largest or the smallest. You may have to do all of them, so parallelizing it may have just been as easy. Okay. Very good. Interesting. This is a little bit like what I was saying, right? Is I think in a specific solution, at least for the examples I gave you, you could do these points, but what they're saying is they Dijkstra'd to like these values right here. So they Dijkstra'd from these to these, and then these to these, and these. And again, when I say like these, it's not like all of these. It's just you say to yourself, am I on this value or this set of values or on this set of values? And then that's like your quote unquote shortest path. Okay. Again, I haven't done C or C++ in like 15 years. So it has changed a lot. Parsing, implement like a point. Point cost comparison. And why would you do that? Let's see. It feels like this is more akin to an A star. But yeah, okay. Rust. Straightforward. Part 2, similar. Horrible. I made a resolution not to peek on Reddit, but I had to because I had no idea how to solve it. Problem twice. Dijkstra from stall. Low. Both left. Is wrong. Yeah, pretty similar. Track that position. Okay. Just do the math. Okay, so this is again, this is the other way of doing it, is like they're looking at the previous radius and making sure like they're, you know, you don't include values that are in the previous radius. So that's an interesting optimization. I don't know if it makes it faster or not, but it's an interesting alternative solution. For me, I was using Windows, which essentially is the same idea, right? As you know, you don't want to do the previous ones, but you do want to do the ones that are in the current. So how do you do that? In this case, it's two like checks, to two math checks. In my case, it's like a subtraction of the previous one that you've already solved before. It probably is 6 of one, half dozen of the other. I suspect. Yes, a lot of people, it looks like they're implementing Dijkstra, especially the Rust solutions, as opposed to like solving themselves. And again, I think I had mentioned this before. It really felt like you couldn't do Dijkstra, or you couldn't just use the pathfinding crate. After I'd whittled it down and refined it enough, I got to the point where I think you could probably use the pathfinding crate. I just don't know how optimal it would be, especially because I think you could, again, like I said, I think you can optimize it to the point where you say, oh, if as I'm moving across both sides, if I ever like run into him, I know I've solved it. I'll definitely try. In fact, I want to add that to my to-do list. What if we short circuit? I check. Well, say I. So I think that actually may be an interesting optimization. So it'd be something I'm willing to try. We just do it for every round. How long did they say it took? 263. So I suspect a lot of these could be parallelized. Be faster, it feels like. Just use Rayon. Just use Rayon. I did have this problem as I was solving it. It was making me nervous because every time I was like trying to solve it, it would say, we're going to refresh. And I'm like, oh, please don't tell me the input has changed. Please don't tell me the input is. Yes. Dual BFS to two specific points to close the circle. Okay. Yeah, I suspect this is like, it looks like a lot of people do the two sides things. I choose the winding numbers. Okay. Very good. Lots of solutions. I actually like solving it the day after, or like at least doing my video the day after, because I think before sometimes I solve it and like no one has, you only have a couple comments. So I actually like doing the videos after because I can see all these solutions and talk through them with you. Okay, so this is probably similar to a winding loop or a winding number. Yeah, okay, so you're just tracking whether or not you've crossed those things. Um, Like at any point in time, if you've ever crossed it, you're done. I think this works the same way. It's a similar solution. I really like the idea of the winding number. It helps make sense in my head, and it's really easy to implement. Like once you've seen it once or twice. But yeah, that's this is a perfect way to do it. Is like have you cross these like boundaries, and so you know you're not done if you haven't crossed them. Okay, that was a fun day. I had a lot of fun doing it. At least sometimes that thing blocks. I had a lot of fun doing it. There you go. You can see it solved in like 70 seconds now. I think on average it's like stuck around the 68, 70, which I feel is pretty good for potentially doing like 20 Dijkstras or whatever. Um, for each radius, right? I think if you look, most of the solutions are like you have to try each radius starting from one, go up, do Dijkstras, and mine was use a winding number. The others were just do Dijkstras on both sides to combine them. That sounds like those were most of the solutions that we were getting. So there you go. Not too bad of a day. I enjoyed it. I had fun. I'd love to see your solutions. If you here's a commenter. So let's read this. I've seen his before. Did I look at this one? Do below the volcano and add some. Okay, we track each tile, whether it's a volcano, the start, or a cell value. That's a cool way to do it. What part of me had thought it might be worthwhile to do something like this. Yep, you can just transition these. This is similar to what I had before. I liked the these are binary, so the bit bytes. In mine I did the is ASCII digit and then converted it to a digit. I guess this has the same net effect. This may be faster. Okay. Data height. Yeah, I think tracking the width and height so you can like bounds checking. I kind of do that too, but I did mine as a function as opposed to the actual value. Get a value at a position. Oh, that's a good point. I don't do this a lot, or I have done it before, like doing indexes into a struct, right? So you can go straight into a grid just by implementing the index. I probably should have done that. I always forget to do that, and I think this commenter has done this before and mentioned, "Oh, here's how I did it." So I need to remember. Also, from stir. I didn't do from stir this time. I just did parse. But from stir is good, especially if you're worried about unwrap. Like you may just have a impl from to get it, but that doesn't return a result. But if you do impl from stir, that does have a result, and so you can return the issue, or if something went wrong. So I've done that before in previous days. I didn't do this one. That would be some good cleanup to do here. Some within radius. Yeah, just that's an interesting thing is I probably could have just done this in line because it's the only place I use it, I think. Oh, I might use it other places, but some by distance. Okay, this is more like what other people were doing, is like making sure that one is within the range. You want to be inside the grid or on the edge of the grid is maybe the best way to describe it. Start left to right. Okay. So is it just Dijkstra's, but you use this state to track whether you start left or right? Left, right. Sounds like it looks like this is like saying once you've been in a quadrant, stay in that quadrant. Is that the idea? Once you've been in a quadrant, stay in that quadrant until you. Yeah, it keeps you in the quadrant. Oh, okay, I see. They're gonna do it both ways. They're gonna do it both sides and then add them. Okay, I like it. Very good. Great solution. Oops, hit my F12. Okay. Um, once again, I think we're at the end. This was a good day. We spent a lot of time talking about it. If you've never used a winding number before, I think it's worthwhile because we have used problems like this, right? Or at least I've seen problems like this before. Is like you want to do Dijkstras, but or like some other pathfinding, but you need to like create a loop. Like in general, it's like Dijkstra with constraints is like the way to think about it. Is like you may you may find solutions, but they aren't solutions that fit the constraint, and you want to like eliminate those constraints. Like I think if you generally understand Dijkstras and you say, oh, I just need to add a constraint, at least in my mind, it makes it easier to solve it. And so that's the way I went about. And again, it's quite possibly not the most optimal, right? 71 milliseconds. A lot of people were talking about solving it in, just tens of microseconds or milliseconds. And so it's possible that it's not the most optimal, but I think it is clearly from the solution. It's an efficient solution, and in my mind, it's easy enough to understand. Much like what this person did right here, right? Is if you use a winding number, it kind of helps you. At least for me, it helps me understand the problem. So let me know though. How did you solve it? What did you do? I'd love to see it. And otherwise, we'll talk to you next time. We're almost done. Just a few more days. So bye, everybody. Have a good day.